Okay, so I decided to go through problems 22, 24, and 31. First problem on the homework, which was a circle. You don't really need to do an input-output table for that where it says r equals, I can't remember what value. It's like r equals 5. You're just graphing a circle at r equals 5. We get into more detailed ones like this where, we're calculating input-outputs. We'll actually go through the plugging in the coordinates, getting out our values. Just a quick reminder that polar setup is a little different than rectangular where we solve for r, but as a coordinate we write as r theta, so like x, y, x is our input typically and y is our output, especially for a function. For polar, it's kind of the reverse, but those are just small nuances, but same idea as you think of theta as an input and r as our output. So when we go ahead and do this, we're just going to plug in values, get out the r value and then graph the points. I decided to go up by pi over 6, or get all of our unit circle values from 0 to pi, and if this is not enough, we can continue on from there. We could also use symmetry, which we'll talk about if necessary. All right, so a lot of this is just going to be verbalization as I plug in values. When I plug in 0, remember cosine of theta is talking about the x value of a coordinate, and when we're doing like cosine theta calculations, we're just thinking rectangular coordinate system. So when I plug in 0, cosine of 0 is saying the x value to 0 rotation, which is 1, and then 1 times 4 gives us 4, so I have the coordinate 4, 0. I'll go ahead and graph that right away. A rotation of 0 and a radius of 4 would put us right there. Next we have pi over 6. So we take the pi over 6, plug it into theta. Cosine of pi over 6 is going to be root 3 over 2, so we have 4 times root 3 over 2, which will look like this. And then 4 divided by 2 is 2, so we have 2 root 3. And so now we have 2 times root 3, and root 3 is about 1.8. So if we multiply those, we get about 3.6. So that means we're going to rotate to here, this axis, that's the 30 degree, and we're going to go out about 3.6, 1, 2, 3, and then a little bit more than halfway. Put us right about there. Next, insert pi over 4. Pi over 4 into here gives us root 2 over 2. So we change this up to a 2. And now that would give us 2 root 2, and root 2 is about 1.4. So I have 2 times 1.4 will give us about 2.8. So I'm going to rotate to pi over 4, which is the middle one right here. I'm going to go out about 2.8. 1, 2, and about 2.8 puts us right about there. If they're starting to see a figure emerge here. Again, that was 2.8. Pi over 3. Plug pi over 3 in for here. That gives cosine of a half, or cosine of pi over 3 gives you 1/2 for the whole ratio. So 4 times a half will give us 2. So we go ahead and graph that. Rotate pi over 3 goes to here, and then we go out 2. I actually have my cursor on that accidentally. There you go. Next we have pi over 2, cosine of, plug in pi over 2 in here. Cosine pi over 2 is 0. 0 times 4 is 0. So we have our origin. We'll go ahead and work on connecting this after. It'll be 0. 2 pi over 3, cosine 2 pi over 3 would be negative a half, because reference angle of pi over 3, second quadrant, so we have negative 2 now. So what will that look like? If I rotate 2 pi over 3, I'm going to rotate 2 pi over 3. And the way I think of it is I've rotated, especially now that I have a negative radius, which means we're going in the opposite direction, and to just make sure we do it correctly, I think that I'm on the 60 degree reference angle in the second quadrant, so 60 degree in the fourth quadrant, since we're going negative 2, so that will go 1, 2, and put us right there. Next we have root 3 over 2. Root 3 over 2 should be negative root 2, so that'd be negative 2.8. And that derives from the fact that if I take 3 pi over 4, plug it in for here, that will give us negative root 2 over 2, which is the same as this, except just the opposite. Remember, we calculated that to be 2.8. This is negative 2.8. So now when I do this rotation, I'm going to rotate to the pi over 4, and of course it's a negative r, so I'm going in the opposite direction. So I recognize I have a reference angle of rotation of 45, so I'm going to do reference angle 45 into the fourth quadrant. So I go 1, 2, and then go ahead and graph it. Oh, whoops, I'm sorry, not 2.8. 2.8. About, try to just graph it as accurately as possible. 5 pi over 6, and if I go 5 pi over 6, that will give us a negative root 3 over 2, so it's going to give us the same absolute value as this right here, but it's negative, so it'd be negative 3.6. So again, practicing this, we go to 5 pi over 6. It's pi over 6 rotation. To help myself go in this direction, I go out 1, 2, 3, 3.6. And then lastly, if I plug in pi, so take pi, plug it in for here, that will be negative 1. Negative 1 times 4 is negative 4. So that means when we rotate to pi here, instead of going positive 4, we're going to go negative 4, which puts us right there, and our graph now is completed. And we end up having a circle. Depending, we want to put arrows, you don't have to, but we can, indicating it's going in that direction. Just one thing I'd like to say about this, if we did symmetry tests, we plug in negative theta and get out the same thing, which tells us that this is symmetrical to the polar axis, and just by graphing this we see that it is. In terms of if these, second point I would make is if this is enough, that's something as we move forward we will generalize depending on the polar equation. In this case it's a circle, as we see it has a diameter of 4, 1, 2, 3, 4, here's the diameter. These types of generalizations we'll be making as we move forward. Okay, on this next one, I suggest distributing in the 4. This is typically the form that we're going to see mostly when we deal with polar equations that look like this. These are called Lie-Masons, as we discussed within the lesson. And the non-factored form is the preferable form. I am going to do I am going to do 0, pi over 6, pi over 4, pi over 3, and pi over 2. I'm just going to start out with that and see where we're at. So first off, just plugging in 0 in for here. Cosine of 0 is 1, so that would be 4 times 1 was 4. 4 minus 4 would be 0. So we have the pole. Then we go to pi over 6. We plug in pi over 6. That would be root 3 over 2. So the calculation will be 4 minus, if we have a root 3 over 2, the 4 over 2 reduces to that. 2 root 3 will give you about 3.4, 3.5. And so 4 minus that will give us 0.5. Next, if we plug in the pi over 4, goes into there, that'll be root 2 over 2. The 4 over the 2 cancels, so it'll be 2 root 2. So in this case, we have 4 minus 2 root 2. 2 root 2 gives us about 2.8. So 4 minus 2.8 will give us about 1.2. I'm deciding in this case to do the whole input-output table and then graph. You decide either way what you prefer. I don't think I'll just verbalize this one. Pi over 3 goes in for here. Cosine pi over 3 equals a half. 4 times a half will give us 2, so 4 minus 2 would be 2. Next, we plug in pi over 2, which would be 0. So we plug pi over 2 in for here. This is 0, so this goes away, and we're left with 4. Let's see what our graph looks like so far. So we have 0, 0. And then we rotate to pi over 6, and we go out about 0.5. I'm going to now zoom in so you can see this a little better. So again, rotation to pi over 6, and then go out 0.5 would put us about right there. Next, pi over 4, so I rotate to pi over 4, and then I'm going out 1.2, put us right about there. Pi over 3, comma 2, comma pi over 3. Oh, whoops, that last one was on the pi over 3. That should have been on the pi over 4. So that goes right about there. Pi over 3, comma 2. So I'm going to rotate to the pi over 3 and go out 2, put us right there. And then pi over 2, 4. I'm going to rotate to pi over 2 and go out 1, 2, 3, 4. And that's what we have so far. We kind of have this curvy fashion going like this. And now I am going to decide to go up to pi. We could go further than that, but after pi we can use symmetry. And if you look up here, if I plug negative pi in for here, that would turn back to cosine pi. So this is symmetrical to the polar axis. So I will see that this problem as well as the next problem are very similar, but what's instructive about them is that the relationship of those two numbers, in this case 4 and 4, and the next one 3 and 4, will give us a interesting shape. And it may seem like an act in futility to go through these input-output tables and do all these values, but it does really help in terms of seeing the progression through an input-output table and taking the physical time to graph it. That it helps illuminate why these graphs behave the way they do based on the algebra. Okay, so now let's look at plugging in 2 pi over 3. This is what's interesting about these. We saw with the other ones, oh, the 2 pi over 3 just mirrored the pi over 3, except it was negative rather than positive. Let's see what happens here. If I plug a 2 pi over 3 in for here, that will give us negative a half. So let's just quickly look at this in terms of the algebra. 4 minus 4 times negative a half. That would turn to a positive 2. And then 4 plus 2 will give us 6. So now we have something a little different going on here in terms of this relative to this one. Next one, 3 pi over 4. We plug that one in. So that'd be 4 minus 4. And when I plug in the 3 pi over 4, that would give us a negative root 2 over 2 for the cosine. So now we have 4 plus 2 root 2. And that will give us about 6.8. And I just plug that in my calculator, but again, you can do those calculations by hand as I demonstrated before. 5 pi over 6 goes in, that'd be a negative root 3 over 2. So we have negative 4, and then we have a negative root 3 over 2. So that would turn to 4 plus 2 root 3. And using the calculator, I got it's about 7.5. Of course, if you did it by hand like I did before, you'd see you get the same thing. Next, we plug in pi in for here. Cosine of pi is negative 1, and negative 1 times the negative 4 is a positive 4, so now you have 4 plus 4, which is 8. This is super interesting, what we're getting here. So let's go ahead and take a look at what this looks like when we graph it. So the next one we're working on is 6 comma 2 pi over 3. So I rotate 2 pi over 3, which puts us here, and I want to go out 6. 1, 2, 3, 4, 5, 6. Obviously, we're going to be off the graph the larger we go. We'll just estimate, though. Next, we have 3 pi over 4, 6.8. So I go to 3 pi over 4, which is my middle one. Remember, if you need help with this, it helps on these that these are dotted. Yours may not be, particularly if you printed it or you draw it up by hand. But keep in mind, if you visually imagine those gone, you just have your 3 scales for your 30, 45, 60 of a unit circle. So it just looks like the unit circle. So trying to recognize the 3 pi over 4 axes in this quadrant, the 3 pi over 4 axes, all you got to do is say, oh, it's the middle one of the 3. So there it is. 1, 2, 3, 4, 5, 6, and another 0.8. Put it right about there. Next we have 5 pi over 6. So I'm going to rotate to the 5 pi over 6, the last of the unit circle rotations. 1, 2, 3, 4, 5, 6, 7, and then 8. We'll put it right about out here. I'm running out of room. Move this over a little bit. So put us right about here. And then for 8 pi, 8 comma pi, we go out 1, 2, 3, 4, 5, 6, 7, 8. Get them off the graph. That's okay. We'll go right here. So we have this sort of behavior. And again, this is symmetrical to the polar axis. So we are going to have reflections of all these points down here. And if I do that, just by sketching, it's going to look something like that. Now, if we, instead of going up by pi over 6, say we went up by like pi over 4s and we went all the way around to 2 pi, we would end up getting this graph. In terms of actually going through that, that's something we'll tackle as we move forward in terms of knowing what input outputs to use depending on the different equations. So as we move on to the last one, we're going to see that this is exactly the same type thing of what we just did, except this 3 and 4 is going to give different characteristics to our graph. So let's go and do the same thing. Let's do input outputs from 0 to pi, and then particularly given that this is a cosine, it reflects it about the y-axis. So I'll just keep talking while I'm filling these in. Now imagine if it was a sine, then it's going to be symmetrical to the pi over 2 axis, like it has this 3 minus 4 sine, for instance. I think it'd be symmetrical to the pi over 2 axis, but actually algebraically it wouldn't work out like that. But in fact it is. It is symmetrical to the pi over 2 axis, which is kind of confusing, but those are kind of some of the nuances that we get with polar equations and graphing them. All that being said, you can just go through grinding it through the input-output table, and of course you can shrink it down to just maybe the zeros, the pi over, it going up by pi over 4 rather than hitting all the unit circle values. Alright, so let's go ahead and plug in. If I plug 0 in for here, cosine of 0 is 1, and then I have 3 minus 4 is negative 1. Next we have pi over 6 plugged in, so that'd be negative root 3 over 2. I'll go ahead and write that. 3 minus 4, whoops, not negative root 3 over 2, just positive root 3 over 2. And that simplifies to be 3 minus 2 root 3. I'll go ahead and plug that into the calculator. We have getting negative 0.46. Of course, we could go through the numerics of why it simplifies to be that. Next would be pi over 4, so that would change that up to a root 2 over 2 rather than a root 3 over 2. So down here, we could just change this up to a root 2, plug it in, see what we get. And this would be a positive 0.7. So positive 0.7. Next, we have pi over 3. Pi over 3 goes in for cosine. This would be a half. So 4 times a half would be 2. So 3 minus 2 would be 1. Next, we plug in pi over 2. So pi over 2 goes in for here. Cosine pi over 2 is 0. 0 times 4 is obviously 0. So 3 minus 0 will give us 3. Next, we go 2 pi over 3. 2 pi over 3 goes in for here. That would make this negative a half. So negative a half times negative 4 is positive 2. Negative 4 times negative a half would be positive 2. So 3 plus 2 will give us 5. Next, 3 pi over 4 plugged in for here will give us negative root 2. And come down to here. So if I do the calculations for 3 pi over 4, it'll look like this. We have 3 minus 4 times cosine 3 pi over 4. Oops, sorry, it was 3 pi, cosine 3 pi over 4 is negative root 2 over 2. And that would simplify the two negatives turn positive, and now we have a 2 root 2. So we have 3 plus 2 root 2 is about 5.8. Next, when we plug in the 5 pi over 6 in for here, that would be negative root 3 over 2. So I'm just going to come here really quick, change this up to a root 3, change it up to a root 3, and then that would change up this to, when we simplify, to a root 3. And then plugging that in the calculator, 3 plus 2 root 3 gives us a 6.5 about. Lastly, when we plug in pi, if I take pi and plug it in here, that gives us -1. -1 times -4 is +4, so 3 plus 4 gives us 7. All right, oops, I wrote 4. I don't know why. Let's change that to a 7. Okay, so let's go ahead and start graphing. Rotation of 0 means we're arrows pointing that direction. -1 for R puts us in the tail direction, which puts us right there. Next, pi over 6. I'm going to try zooming in here. So if I rotate pi over 6, that's a pi over 6 reference angle with a -R, so I'm going pi over 6 in this direction. 0.4 is about halfway to the 1. Next we have 0.7, so I go pi over 4, I rotate pi over 4 and then go out 0.7, puts us a little closer to the 1 than the last one. Next we have pi over 3, 1, so I rotate to pi over 3 and put 1, and then pi over 2, 3, puts us out here. So we see we have this sort of behavior happening. I didn't get that last point really well, but you hopefully get the idea. Next we have 2 pi over 3, out 5, so I rotate to 2 pi over 3 and then go out 5. That would put a point right there. Next 3 pi over 4, 5.8 would be right about there. 6.5 at 5 pi over 6 would be a little out past it. And then this will be even more out past it at 7. So we have this sort of thing happening. Now, if we reflect this, and this is reflected about the, or symmetrical about the polar axis, we would have the same sort of behavior going like that. And of course, if we did more points from 0 to 2 pi, we would see those evolve the same, probably a little more accurate. And note, I did miss that one, but hopefully you get the idea. And what's interesting about this is this graph here has this inner loop versus this one where it kind of just has like a heart-shaped. And we'll talk about those relationships as we move forward as far as how these numbers, the 3 and the 4, whatever those may be, how that affects the shape and where these graphs are.